quarks and antiquarks. And I'm just going to say right from the off that I pronounce the word quarks, but I have heard it pronounced quarks, and people will passionately claim that their pronunciation is the correct pronunciation. In truth, it doesn't matter whether you say quarks or quarks. It really doesn't matter. I was taught by somebody who said quarks, and that's what stuck. So we had this puzzle, didn't we? We had this puzzle with particles like kaons that lasted too long. They had too long a half-life, which was quite a mystery. These particles seem to come into existence in pairs and then disappear very, very quickly. And so because they came into existence in pairs, we ended up with these V-shaped tracks from those particles. Probably the only way we could describe it, these V-shaped tracks. So if I had a particle here, there's my dot, there it is, it would decay into two particles, leaving this V-shaped particle, and then this would decay into two more, and this one here might decay into two more, like this. And by examining the properties of these particles, we might find that that one and this one are of a different nature, because the one on the left ends up decaying into a proton and a pion, and the one on the right only decays into two pions. So we know that the one on the left is a baryon, the one on the right is a meson. But the half-life seemed a bit too high for these particles, given their mass. So what was going on here? What is special about these sigma particles and these kaons? Well, sigma particles, which are baryons, because they decay into protons, and kaons, which are mesons, because they don't decay into protons, are, and the word we use is strange. So rather than saying are, we can say have a property called strangeness. And I'm struggling to spell, as always, strangeness. Now, the first particle that was discovered that was a strange particle was the K plus meson. So the K plus meson, we say, has a strangeness, and it is a property, is a real property, has a strangeness of +1. And so our K minus property particle has a strangeness of -1, which is fine until you get to things like the K0 particle, because that doesn't have a charge. So if we say K plus has a strangeness of 1, K minus has a strangeness of -1, you might think K0 has a strangeness of 0. Well, it doesn't. It has a strangeness, whatever that means. This property has a strangeness of +1. How very peculiar. But there was a neutral kaon, which we call an anti-neutral kaon, which has a strangeness. I keep spelling strangeness without the S. That's obviously incorrect. Has a strangeness of -1. Quite a riddle. I'm sure you'll agree. Quite a riddle. Now, we've decided what these particles are, these strangenesses, based on their properties, based on what happens, based on how they interact. Based on what interactions are possible and what interactions are not possible. So if we take, for example, if we take a pion, a negative pion, and we collide it into a proton, we can actually cause high energy particles like the kaon, the positive kaon, and the sigma minus, to form. We can make that form. That's possible. That does happen. So let's put a big green tick next to that. That is observed. And maybe I should write next to it, is observed. We see that happen. But oddly, what we never see happen, even though it looks like it should happen, is a negative pion colliding with a neutron. So you see we've got charge of negative, a negative kaon, plus a neutral sigma particle. We never observe that. It's never observed. So you might think to yourself, oh, okay, maybe we can't get neutral sigma particles. That would be one explanation, except we do get neutral sigma particles. If I take a pi plus particle and I collide it with a neutron, then I can create, in this interaction, a K plus and a neutral sigma. That is observed. What a mystery. So what's happening here? Why is it that I can observe sigma 0 particles, but only if they're created with positive kaons, not negative kaons? And we know all the properties of these particles because we can put big, strong magnetic fields and see what happens with the particles, the paths they trace in those magnetic fields to work out their charge. This is what we can do. And by the pitch of those circular paths, we can tell what the specific charges are, that sort of thing. Another one that is observed is if we have a negative pion colliding with a neutron. So remember, this is what caused us to have a not observed interaction before, but we can get K0 and we can get the negative charge going on to the sigma particle. That is observed. Wow, this is a riddle, isn't it? Imagine being faced with that. We never see that second interaction happen. So what is going on here? We've numbered strangeness for a good reason. Let's have a look at the sigma particles. Let's give sigma particles strangenesses as well. Let us say, let's just draw a line down here to separate what's going on. Let us say that sigma plus particles actually have a strangeness of -1. Now, if we do that, this can work. And you'll notice I haven't actually included any sigma plus particles in those 4 examples. Let's say a sigma 0 and a sigma minus all have strangenesses of -1. All the same. Now, we can get antimatter sigma particles with positive strangeness, but matter sigma particles only ever have -1 strangeness. Now, if we do that, for each of these interactions, let's number them 1, 2, 3, and 4, we could have a look at what charge is doing, and I'm not going to leave notes on this because we've kind of checked this already. Is charge conserved in each of these cases? So we could say negative plus positive is neutral, positive plus negative is neutral, so charge is conserved there. Negative plus neutral, charge is conserved there, and so on. Charge is conserved with them all. And we could check what's going on with our baryons. Well, these are all baryons and those are all baryons. So we're not losing baryons in this. They're just changing from one type to another. But what's happening with the strangeness? What's going on with that? Well, pions have a strangeness. Oops, let's get the pen out again. Pions have a strangeness of, and let's just write down here a subtitle, strangenesses. Strangeness. answers, like that. So pions have a strangeness of 0, plus protons have a strangeness of 0, which forms K plus, which we said had a strangeness of +1, and sigma, what's that one? Sigma minus, which has a strangeness of -1. And you can see that that works. They balance. But if we take the second example, and we say pions have a strangeness of 0, neutrons have a strangeness of 0, K minus had a strangeness of -1, and sigma 0 had a strangeness of -1. Does that work? Well, no, that does not work. So it seems to be that we can create, and check the other two yourself if you want, it seems to be that we can create equal amounts of positive and negative strangeness. Can create equal amounts of positive and negative strangeness. Well, how very interesting, and you can check the rest of them yourself. So what does that mean? Well, it sounds a bit like we're saying strangeness is conserved. Actually, that's not quite the case. In this interaction, in this particular picture, it is a strong interaction. In strong interactions, strangeness is indeed conserved. So let's put this in strong interactions. Strangeness is conserved. However, kaons decay. Look back to this. In this picture at the top, remember that we had our kaons. We saw kaons, here they go, here are these kaons, but they decay into 2 pions. And the pions don't have strangeness. The strangeness is 0. So what's going on here then? Well, it looks like there is an interaction that causes strangeness not to be conserved. For example, this sigma particle decays into a proton and a pion, neither of which has strangeness. The strangeness can vanish. The strangeness is created in equal amounts down these 2 branches there, and we can do that with a proton colliding with a pion or a neutron colliding with a pion. We can do that with either of those, but then that strangeness seems to vanish all by itself. It's not conserved in this other type of interaction. And the type of interaction we are talking about is the weak interaction. In weak interactions, sometimes we think of those as decays. Strangeness is not conserved. That is not to say that you might have a weak interaction where strangeness is the same. That can happen. We can get strangeness that happens to be the same, but that doesn't mean it's conserved. Conserved means it's always going to be the same before or after the interaction. And that is not the case here. Weak interactions, strangeness is not conserved. And weak interactions are sometimes called decays. Although I'm going to put sometimes here because we can actually have composite particles decaying by the strong interaction. But I don't think that really comes up as a topic on your A-level. So how do we solve this riddle? Well, we're going to solve this riddle with a chart. It's not a lovely chart. It's actually one of my least favorite charts, but here we go. We're going to put on this chart all the pions and all the kaons that we've got in a particular order. Remember, a big part of science is taxonomy. That is sorting things into categories. And so here we've got my pions running down the middle. And if I place my K0 up there, and this other particle, this K0 with a bar over the top, down there, I can also place my K plus up there and my K minus down there. Now you can see we've got some sort of pattern here. There's some sort of structure. These particles down here have no strangeness. These particles both have negative strangeness, and these particles both have positive strangeness. So we could label them +1, -1, 0, and let's label that strangeness. So we're sorting our particles into categories. We also have charge. So I could look along here, I could look along here, and I could look along here. And now I've got -1, 0, +1, and that would be charge. Just like that. Now, looking at a diagram like that, a hexagonal diagram like that, and trying to unpick what might be the underlying cause is the work of a genius. 𝗟𝗶ሔር𝗸𝘀, sometimes pronounced Gell-man. 𝗟𝗶ሔር𝗸𝘀 figured this out, and it is genius how he figured this out. He decided, and by the way, the particle zoo got a lot bigger than this. I'm only showing these particles, but we've got all sorts of other particles thrown in the mix here as well. And these are only mesons that are being shown in this particular diagram. Maybe I should write that down. Let's write that down. So mesons. We're just trying to make sense of the mesons. He decided that actually these mesons were not fundamental. They're not fundamental. That means they have structure. They contain something. Unlike mental. Do you know what? I think fundamental is one of those words I need to write a definition for. Not fundamental. They contain something. They have other particles inside them. And by some, I don't know, genius inspiration, he figured out that your pions contain two types of quarks. This is a down and an up antiquark. This is an up and an up antiquark, or it could be a down and a down antiquark, or it could even be something else, which we'll come to later. This one over here is an up anti-down quark. And you said there must be another one. This one up here is going to be a down anti-strange quark. This one up here is going to be an up anti-strange quark. So anything with an anti-strange quark has a strangeness of +1. He said down here, this is a strange anti-up quark. This is a strange anti-down quark. And so anything with a strangeness of -1 has a strange quark in it. And he said mesons contain one quark plus one antiquark. Just fit that on the side of the screen there. That's what mesons contain. They're not fundamental. And he said, well, baryons aren't fundamental either. They contain quarks. Baryons don't contain any antiquarks. So remember, matter and antimatter annihilate. Well, here we've got these particles, these mesons, that contain matter and antimatter. That's why they don't stick around forever. But protons do. So they don't have any antimatter inside them, said 𝗟𝗟𝗀𝗀. Neutrons turn into protons. They don't have any antimatter inside them. So he devised a system of quarks and antiquarks. And it involves a table. I mean, this is the title of the lesson anyway, but I'll put it as a subtitle. And it's a table of particle properties that you are, in fact, given in your exam, which is shameful. You should know these lists. So he looked at three properties. Charge, let's label it. And let's use color coding. So charge, which we'll use the letter Q for, strangeness, and we'll use the letter S for that. And one other thing, we're going to call it baryon number, because he figured out that the reason why, let's just put that as a B, he figured out the reason why these things stick together the way they do is because you always get 3 quarks in a baryon, 3 antiquarks in an antibaryon, and a quark and an antiquark together in a meson. Now, the real reason why it's 3 in a baryon is complicated, and I'd love to go into it, and I do go into it in my history of the standard model lecture series. It's about 2 hours long, and it's definitely worth watching, I think. But I'm not going to go into that now. We're just going to make a statement of fact that you need to learn. So we've got up quarks. We use the letter U for that. We've got down quarks. We use the letter D for that. And we've got strange quarks. We use the letter S for that. And you've already met these letters on this hexagonal diagram. We also have their anti-equivalents. So we've got an up antiquark, a down antiquark, and a strange antiquark. I shouldn't have said equivalent, I should have said counterparts. They're antiparticle counterparts. And we can start filling in our numbers. And it is definitely worth memorizing this list, even though you're given it. Why is it not let me draw this line across there? There we go. So let's start with charges. Well, look at the diagram. Look at the K plus. It has a charge of 1 elemental charge unit. That's 1.602 times 10 to the negative 19. So all these charges are going to be in terms of proton charge. And if a proton contains 3 quarks, then you'd think that there must be multiples of 1/3 of a proton charge inside the proton. These 3 quarks each should have some multiple of 1/3 of a proton charge. Well, the quarks have got a multiple of that. The up quarks are actually 2/3, with the down quark being negative 1/3. We'll come to what's interesting with that in a second. Strange quarks, the properties are almost the same as for down quarks. Strange quarks are really similar to down quarks. Strangeness of these two is 0, but the strangeness of a strange quark is negative 1. That's the difference. They all have the same 1/3, 1/3, 1/3 baryon number. So I could combine 3 quarks, any 3 of these quarks together, and make a baryon, because 1/3 plus 1/3 plus 1/3 is 1. So when we add our quarks together in a composite particle, like a proton, like a neutron, like a sigma particle, what we do is we add together these quantum numbers. That's what we call these things. The antiparticles are exactly the same, but all the quantum numbers are reversed. So if I get a quark and an antiquark together, the baryon number is 0. That is why they are not baryons, they are mesons. So these both have 0, but this is plus 1. Do I need to write the plus if it's just 1? Maybe I should to emphasize it. No, I'll just write 1 and you're going to like it. Or not, I don't care. There we go. Right. Then green for the charge. These are all reversed. That's negative 2/3. Positive 1/3, positive 1/3. So you can see all the quantum numbers are reversed. They're called quantum numbers because they have these discrete values. All reversed for antimatter. And that's it. That is what our quark model shows. So if I have a proton, it has a charge of plus 1. That means it contains an up quark, an a down quark. Check it for yourself. Let's check the charge. So let's say 2/3 plus another 2/3. That's 4/3. Subtract 1/3. That's 3/3. That's plus 1. that works. Strangeness is 0 plus 0 plus 0. Baryon number is a third plus a third plus a third. The proton is indeed a baryon. It does indeed have a quark structure like that. Neutrons, on the other hand, are up, down, down. Check the charges. Plus 2/3, plus negative a third, plus negative a third. Makes 0 charge on a neutron. And the baryon number is a third plus a third plus a third, and they're not strange. Our sigma plus particle, sigma plus, well, that's going to be an up, and a strange. And it works out. Our sigma 0 is going to be an up, a down, and a strange. Our sigma minus is going to be a down, and a strange. And you can check these properties. You can check the charge, and you can check the baryon number, and you can check the strangeness, and it works out. Now, that's the tip of the iceberg. There are lots more particles than that. But now we can see that there must be something that is changing these quarks from when the ones that are in sigma particles that contain a strange quark into, let's say, a down quark or an up quark. And that is the work of the weak nuclear force. Now, you've met the weak nuclear force already for beta decay. Let's just draw a normal beta decay. We've already met our diagram for the beta decay. We have our electron coming off like that. We have our electron antineutrino like this. We have our proton like this, and we have our neutron like this. Well, what's actually happening in this decay at the quark level? Let's get rid of the neutron and proton then. If we go from neutron to proton, from here to here, let's get the pen out, from here to here, from neutron to proton, the one that changes is a down quark changing into an up quark. That is what happens inside our particle. That is our beta minus decay. And for beta plus decay, it's completely the opposite. It's an up quark changing into a down quark. And remember the reason why I did the arrow backwards for the antimatter, Feynman's interpretation of antimatter. So we've covered quite a lot here, and we've introduced the idea of quarks and antiquarks. Next lesson, we're going to look in more detail at those conservation rules. We might even introduce some new particles, or maybe we shouldn't overload you with new particles, but I think we should. There's only one lesson left about quarks and leptons. Hopefully you found that useful. Tune in for the next lesson.